Greetings, chemists. Lecture today will be on thermal energy. And let's start. We're basically talking about heat as the general topic here. And let's start with a definition of systems. When we talk about in science, very often it's common to not look at the whole world all at once, but to take a specific part of the world that's simple and easy to understand, which we can then go into more and more complex detail about later. So I'm going to start with a pot of water on a stove, in which I leave the lid off and I light the burner underneath. And I'm looking specifically at the energy flow regarding this system. I know the heat goes into the pot itself, the walls, because if I ever touch the pot, it's very hot. I know energy's coming out. I can feel it there. It's coming out the sides, right? It goes out this way. It goes into the pot itself. And when the pot gets hot, it heats the water inside. I know this. If I ever dip my hand in there, that's going to hurt because, I'm basically getting cooked. But I also know that if I put my hand up here above the pot, that there's energy coming out the top of the pot. Okay? And if I leave this pot on the stove for a very long time, actually the water will start to decrease. We'll get lower and lower water levels in the pot. So molecules of water are apparently able to leave the system. And other things are able to go into the system. I could add, carrots into the pot or something, whatever I'm cooking. We would call this, if the system is the pot, we would call this an open system. Open, in this case, refers to the fact that both energy and matter can enter or leave the system. So the system is the thing I'm studying, in this case the pot. Energy, like heat, can flow in. It can also flow out. We can see that both of those things are happening here. And matter can flow into or out. I can put things in. I can, water can evaporate. I can pull things out with a spoon or something. So this is called an open system. Okay, let's take another example. Let's say that I take the same pot on the same stove, same water, but I put a lid on it, a nice tight-fitting lid, maybe like a pressure cooker lid, and clamp it down. And I heat that thing here. Well, that pot, energy is flowing into it. So we can see the energy. If I touch the pot, it gets warm. And it's actually getting to the stuff inside, like the water, right? If I were to take the lid off after, 10 minutes or something, the water would be boiling. So energy can get to the water. However, the water can't evaporate out because the lid's in the way, and I can't put stuff in because the lid's in the way. We would call this a closed system, the system being the pot. Okay? The pot is a closed system because energy can enter or leave the system, but matter or molecules cannot. So within this closed system, mass would be conserved. We would have the same amount of mass after a long period of time. If it was a truly closed system, right? Obviously, there's going to be varying levels of that, but if you have a weakly fitting lid, you might get some air escaping, so it'd be mostly closed. But if you had a nice tight fitting lid, you could be pretty confident that it's a closed system. And let's take one more example, which is a thermos. Thermoses are specially designed to have two walls, an outer wall and an inner wall. They have a lid, which has also got a layer inside of it. And when they design the thermos, they suck all the air out of the insides of the wall so that there's no molecules there. Okay? And then they fill it up with your coffee or your iced tea or whatever it is. If you want it to stay hot, you put something hot in there. If you want it to stay cold, you put something cold in there. But that thermos actually is designed so that when energy tries to leave the system, it can't. And it has to do with that vacuum, which we're going to talk about in a further lecture video. Actually, we might talk about it at the end of this one, why that happens. It's a good segue. This system would be an isolated system. The system of the thermos would be an isolated system because neither matter nor energy can enter or leave the system. All right? So those are the three types of systems we will be dealing with in chemistry. And we, again, always in chemistry, we want to take it to the level of the molecule. What's happening at the level of the molecule? And I'm looking at the thermos here. This thermos is sort of instructive as to how energy is transferred in the first place. It needs molecules for the most part, unless you're a piece of light. Okay? As long as you are a hot object, you can make another object hot, but you have to be able to touch them here. And so what we do is when we suck the air out from in between that layer of the thermos, we're saying there's no way that this hot piece can touch this piece here to transfer that heat. So let's talk about ways that we transfer heat. Okay? One way is to get two hot things to touch. So let's say I have a fire. This is how they used to brand cattle, right? They would take a big piece of iron, and you would have your brand name on the end of the iron, and you would put it in the fire, and it was very, very, very hot in the fire, and this would get very, very hot, and you had to be careful. You had to use gloves when you were holding onto the handle, or you would get burned too, and they would press that into the cow, and it would transfer, because all the molecules here are hot, and they would touch the cow's molecules, get really hot, and brand it in there. You could argue whether or not this is humane, but this is how it worked. When two things touch, we call this conduction. Heat is transferred when molecules touch. And it's generally assumed that they are solids, I think, and I'll say about why in a moment. But let's keep going. Let's go back to our pot of water analogy. Our pot of water that was sitting over the heat got very hot, and it started to boil, and then steam started to rise up above it. And if you were to put your hand here in the path of the steam, if you've ever done this over a stove, you would feel the steam. Your hand would heat up. Okay? Because the molecules of steam are kind of swirling around your hand. Okay? The flow of like a gas or a liquid or something that contains hot particles that causes something to heat up, we refer to as transferring heat by convection. It's like a current of heat, a flow of heat, as opposed to a solid piece of heat that you're just touching, right? So convection would be the flow of hot gas or liquid particles. Now, to be perfectly honest with you, it almost sounds like convection is another type of conduction. You're still touching the particles, at least in my mind you are. But because they're fluid, because they are not solid like these, it happens at a different rate. Maybe that's a pedagogic distinction or a pedantic distinction. Anyway, we'll talk about the flow of something as being a convection current, and we'll talk about the touching of something solid as being a conduction interaction. And both of those are sort of blocked off in the thermos, right? In the thermos, when we take those molecules out, nothing can flow between and nothing can touch directly. So we lock out convection and we lock out conduction. However, if you have a thermos and you put coffee in it and you leave it for several days and you go to test it, it actually does cool off a little bit. We could ask why this is the case. There's probably a little bit of the fact that this solid is connected to the lid and the edge of the lid. There's probably some conductive pathway to the outside. So it's not completely blocked off. But nevertheless, there's another reason why you can still get heat to transfer. And one, let's think of a very much bigger example, which is the fact that we on the Earth, on the surface of the Earth, every day get very warm and every night get very cold, and the sun is way far away from us, and in between us there are no molecules. Space is a place where there's basically zero molecules. There's some, but they're so far apart that it certainly doesn't account for how warm we get from the fact that the sun gets to us. So without molecules between us, we're like our own thermos. So how can we absorb energy from the sun if there's no molecules to touch or with no convection currents or anything like that? Well, the sun is producing light rays. And light can carry energy even when there's no molecules, right? Light itself is not a molecule. We're going to get into the idea later that there are maybe things called photons, which are sort of like particles of light, but they're also sort of like waves of light. So at any rate, in the traditional sense, light is not a molecule, and so it doesn't have mass. It can't conduct and it can't convect, but it can carry energy. The way that light carries energy, we describe this as a radiation effect. Okay, radiation is a wave, basically, a wave carrying energy. It's an electromagnetic wave. And waves don't need matter. So your hot drink can radiate heat waves across that gap, which is a small part, but still will cool your drink off over time. So anything warm gives off infrared rays, which are pieces of light. And there are certain animals that hunt at night that have learned or have adapted, I suppose, their eyes to be able to see those infrared rays to make it easier to hunt things that are warm. Right? Let's talk about molecules again. So we have this idea that molecules can conduct, can convect, can radiate. And the heat that they contain, let's think of a sample of molecules. So let's think about water molecules in a pot. And I'll just draw them as little dots. Pretend this is your pot of water. And I'm going to heat it. So before I heat the water, they're kind of in the pot. And after I heat the water, what we think of is that we have increased their movement. So when you have water molecules sitting around, they're not idle. They move around. They bounce around. I'm not going to draw arrows on all of them, but you get the idea. There's a general movement of water molecules. If we heat the pot up and give them energy, essentially transfer energy into there, they move faster. So these arrows get longer. Okay, as opposed to these little arrows here. So hot things are generally assumed to be moving faster than cold things. This is known as kinetic molecular theory. Kinetic is associated with movement, okay? So an object with more movement energy has more kinetic energy. And an object with more heat, its molecules have more kinetic energy. So transferring heat to a system of molecules gives the molecules more or greater kinetic energy. All right. And that is enough for this one. See you next time.